Greetings from Hannover and welcome to the presentation with the title Systematic Design Method for Asymmetric Multiport Antennas based on Characteristic Modes. Before I go into the details of this work, I would like to start with some background information about the project behind this work. And this project is part of a priority program of the German Research Foundation aiming at achieving ultra-high data rate communication wireless systems about 100 gigabits per second and beyond. And in our part of this project, we try to achieve these goals with a massive MIMO approach below 10 gigahertz at frequencies below 10 gigahertz. And in order to design compact antenna elements, we apply multi-mode antennas designed by means of characteristic modes. Here we see a demonstrator from 2016, a multi-mode antenna with 4 ports based on a square geometry. And in the last couple of years, we focused on the base station antenna design, first of all, because we are at the base station, we can design the geometry freely. We are free to decide the geometry at will. And we have recently found that symmetric antenna geometries are especially suitable for the task of designing multi-mode antennas, because we can show on fundamental basics by means of group theory that symmetric antenna geometries offer mutually orthogonal sets of characteristic surface current densities. And these orthogonal sets can be excited separately, and this leads us to the design of perfectly uncorrelated antenna ports. In order to achieve this, we have to symmetrically place our feed points on the antenna surface. Here we have used such excitation slots. And what we additionally need is such a feed network which distributes the input signals to these feed points. And with this design approach, we can design a 6-port multi-mode antenna based on such a square geometry. And we can push this even further. For example, on a hexagonal plate, 8 ports would be possible. So this is the base station antenna design, and this is quite well understood, this symmetry-centered design approach. But what about the mobile terminal or user terminal, so the terminal at the other side of the massive MIMO link? Usually we want to use some given geometry, for example, the chassis of a smartphone or the housing of some device. And there we cannot decide freely about the antenna geometry. So we have to live with what we get. For example, let's consider a simple model for a smartphone chassis, such a rectangular plate. Here again, we can apply our symmetry-centered design approach, which yields us 4 orthogonal antenna ports. And in order to realize these 4 ports, we have to distribute our feed points symmetrically on the structure. And here we again we need a rather bulky feed network, which would stretch across the entire geometry. And space is strictly limited in such at the user terminal. So this might not be the best design approach for this. And what about asymmetric antenna geometries? What about the case if we cannot apply this symmetry-centered design? And these questions are the motivation for this work. So what are the goals of this presentation? First of all, we want to understand what consequences asymmetric antenna geometries have on multi-mode antenna design. Additionally, we want to avoid these bulky and complex feed networks. So we want just 1 feed point per antenna port. In this case, we can completely avoid such a distribution network. And of course, we would like to have a systematic design approach. And this is where the characteristic modes come into play. So this is the outline of this presentation. We will have a closer look at the consequences of the antenna asymmetry on characteristic modes. Based on this, we will propose a port placement procedure, which will be illustrated by some numerical examples. So let's begin with some theory. I would like to start with the fundamental fact, which is that the characteristic surface current densities are basis functions of the so-called irreducible representations of the symmetry group of an antenna. This is the fundamental fact which links the theory of symmetry with the theory of characteristic modes. And this was already shown in the 70s. And recently there have popped up a lot of interesting applications of this connection. So what can we learn from this for our asymmetric antennas? First of all, the symmetry group of an asymmetric antenna simply consists of the identity operation. There is no symmetry transformation, which is rather intuitive, of course. And this simple symmetry group has one irreducible representation whose matrix is 1. So this simply tells us that the characteristic surface current densities remain unaltered. So why do we apply here this complicated terminology? Because there's a fundamental orthogonality theorem from group theory, which tells us that the characteristic surface current densities belonging to different irreducible representations are orthogonal to each other. However, here we've got only one irreducible representation in the asymmetric case. So we can conclude in a general way, and that's why we have got this complicated terminology, we can conclude in a general way that all characteristic surface current densities on an asymmetric antenna are correlated with each other, at least to some extent. And this has direct consequences on the multi-mode antenna design, on the excitation of characteristic modes. As I told in the introduction, for symmetric antennas, we need such symmetrically placed feed points. So the antenna port has to represent the symmetry. Of course, this is not possible for an asymmetric antenna. And furthermore, we can conclude from the slide before that virtually any excitation will couple to each characteristic surface current density, at least to some degree. So perfectly uncorrelated antenna ports will not be possible on an asymmetric antenna. However, the orthogonality theorem does not tell us anything about the amount of correlation, so it might still be possible to minimize the correlation, the port correlation, measured by means of the envelope correlation coefficients. And this idea is motivated by the fact that we can express the envelope correlation coefficients by means of the modal weighting coefficients here. And yeah, this means we can express it by means of modal parameters alone. And that's the motivation for our proposed port placement procedure. So we want to minimize the ECC expressed in terms of the modal weighting coefficients. And yeah, let's assume we've got some geometry given, some asymmetric geometry, for example, this L-shaped plate. And we start with performing a modal analysis traditionally. And now we can just place some voltage gap source on one of the mesh edges. And we can readily compute the modal weighting coefficients as a simple post-processing step. So this is known. And now we can place a second voltage source on some other mesh edge and compute the ECC based on the modal parameters. This is again simply a post-processing step. And this enables us to perform an exhaustive search. So we simply try out all possible positions for the voltage gap sources and this way minimize the ECC. And of course, this is a very simple approach because it's just an exhaustive search, but it's comparatively fast because we work on modal parameters alone. So we just need one simulation run for the modal analysis and then it's a simple post-processing. So let's illustrate this procedure by means of some examples. Again, this L-shaped back plate. We have to decide some or choose some design frequency. We have to set our maximum ECC, maximum allowed ECC, for example, to 0.2. And here we take into account 12 modes. These are the modes with eigenvalues between -100 and +100. And in this setup, our proposed procedure yields 4 antenna ports consisting each of one gap source as shown here. We can now analyze this port configuration by means of the modal weighting coefficients, which is shown here. And we see some sort of mixture of modes is excited by the ports. Especially every port excites every mode to some extent, which was predicted by the theory. Otherwise, it is quite difficult to tell what's happening here. So let's go on directly to the envelope correlation coefficients, which show that indeed our 4 antenna ports are only weakly correlated as desired. So what can we learn from this? Obviously, the successful strategy consists of exciting some weird combination of characteristic modes, which add up destructively when computing the ECC. And of course, this would be hard to find manually, for example, by expecting the characteristic surface current densities. And what our procedure does basically is automate this design process what we usually would do manually. Can we use this for practical design? In order to analyze this, we have replaced our voltage sources, our ideal voltage sources, by such electrically small slot excitations. We have used two-component matching circuits to perform impedance matching. And this looks, for example, like this. We can now, again, analyze the correlation, and we see the correlation coefficients have not changed a lot. The low correlation is preserved as we have not changed our antenna geometry significantly. Furthermore, we can show indeed we can match all 4 antenna ports simultaneously. So our procedure is basically applicable to a practical design. In order to corroborate this, we can have a look at a more complex 3-dimensional object with some asymmetry introduced here. The setup is basically the same, and our procedure yields, in this case, 6 antenna ports, and we have directly applied here these excitation slots as shown here. Again, let's analyze the port correlation, and we see indeed our 6 ports are only weakly correlated, fulfilling our maximum ECC criterion. And again, we can achieve impedance matching simultaneously for all 6 antenna ports. So again, this is a practically feasible example. However, we have to have a closer look at the mutual coupling because it may become relatively high. So it seems to be more restrictive than the correlation. And this has to be taken into account in a future realization. And with these results, I would like to give a short summary. So first of all, we had a look in a general way on the consequences of asymmetry on multimode antenna design. We've shown perfectly uncorrelated antenna ports cannot be realized. However, we can try to minimize the correlation in a systematic way by means of or by using characteristic modes. And especially our proposed procedure only needs one full simulation run in order to perform the modal analysis. And then it works on the modal parameters alone. And another advantage is that we only have one feed point per antenna port, and we only need 2.2 port matching circuits instead of the complex feeding networks in the symmetry-centered design approach. And we have shown 2 examples which are practically feasible. So what could be done in the future? Yeah, we have to have a closer look at mutual coupling, of course. We could optimize our procedure with a more sophisticated algorithm and influence of mesh density, of course, but that was not the point of this work. The important point is that we can optimize our antenna design by means of characteristic modes, and this is a general goal or a long-term goal, that we use characteristic modes towards a more generalized and more automated design procedures. Yeah, with this promising outlook, I would like to thank you for your attention. And yeah, are there any questions?
Okay, thank you very much, Nikolai, for this interesting presentation. We are on time, so we have time for a couple of questions. You know, you can raise your hand if you want to ask a question.
Yes, please go ahead.
Okay, yeah. So thank you, Nikolai, for the great presentation. My question is, when you excite on your antenna aperture and you try to calculate the ECC, are you using a port X, like an external probe to excite the aperture, or you are exciting the edges in the mesh?
In the procedure itself, we use voltage gap sources. This is, they are placed on the mesh edges.
I see. But I'm not sure, but when you put a voltage source directly on the plate, isn't the source kind of shorted?
Yes, it is very badly impedance matched, of course, but it is still able to excite a current density on the plate. And that is why we can evaluate the modal weighting coefficients. So this is possible. Of course, impedance matching is not possible with this approach.
Okay.
I see. Thank you.
Any more questions?
Yes, we have got another question from Hanye.
Hello. Thanks a lot for your interesting presentation, Nikolai. So based on the numerical examples that you showed for asymmetric antenna, in order to find the proper semi-uncorrelated parts, in my opinion, we can conclude that CMA doesn't really help us to give an insight for asymmetric antennas, because at the end you are doing some optimizations in a blind way in order to find the uncorrelated ports, and then you're not really benefiting from the CMA to give you some insight about the modes. Do you have any, comments about this, or? Yeah. Thank you.
Yes, I understand your point. You are right. We have not, or we are not using the current densities to get some illustrative insight, but we are still working with modal parameters, and that's where I disagree with you. We use modal parameters. We can see this on this slide. What we are basically doing is that we automate the process we would usually do manually. So manually we place the port and evaluate the weighting coefficients, and this step is automated here. So we haven't got this insight from the characteristic surface count densities, but still we are exploiting all we can get from the characteristic modes.
Yes. Okay, I see. Thank you.
There is probably another question from Huili as well. You can go ahead.
Thank you, Divisa, and thank you very much for the presentation. I have a question. I saw that your mesh is very, very dense for this structure, though the structure is very simple. So is there any reason for this dense mesh?
Yeah, we haven't, or we didn't go too much into the mesh density. That is why I put it on the last slide. This would be something to investigate further. Here I chose a dense mesh in order to to have as many possible positions as possible, as many positions as possible. The effect of the mesh density has to be investigated further.
Thank you very much.
Okay. Hassanen, you've got a question? You can go ahead.
Yes, thank you. Just a quick one. Have you prototyped any of these examples and measured them?
No, we haven't so far, I have to admit. But I would claim that this one could be prototyped rather simply.
And when you will measure this one, what is your reference ground reference? Sorry.
I would use the antenna plate itself as the ground plane and use microstrip lines to feed the slots.
Okay, so there will be some locating probes in those slots. Is that correct?
Yes, for example, a microstrip to slot line transition.
Okay, thank you.
Okay. I think we should go to the next speaker.
Yes. Yeah, thank you so much, Nikolai, once again for your presentation and for the interesting discussions afterwards. So let's move to the second presentation now, given by Huli on the pattern synthesis for single antennas using TCM. So you can share your screen, Huli.
Thank you, Divisa, and thank you for everybody. I'm very glad to be here to present my work. My name is Hui Li. I'm from Dalian University of Technology, and my topic today is pattern synthesis for single antennas using the theory of characteristic mode. And this work is carried out together with my master student, Sining Sun. And my topic will be divided into 4 parts. First will be a simple background, and then I will describe the pattern synthesis method for the 2D and 3D structures, and followed by the conclusions. As we all know that the radiation pattern is one of the key parameters for antenna design. However, for different applications, different radiation patterns are required. For example, for a radar car antenna, and the radiation pattern of the antenna should be pointing directly forward. And for shipboard antenna, for communication application, it needs low elevation angle. And for mobile phone antennas, it needs omnidirectional radiation so that the signals from anywhere can be well received by the mobile handsets. However, the pattern synthesis is normally carried out for the phase arrays, and there are not many literatures dealing with the pattern synthesis for single antennas. And but fortunately, characteristic mode is one of the useful methods for pattern synthesis. And there are some literatures dealing with the pattern synthesis for single antennas. For example, Professor Yikai Chen has proposed characteristic mode pattern synthesis for the UAV antennas, and Professor Benhard has also used the impedance matrix to design antenna with a certain characteristic far field. And also some literatures also use a phase shifted characteristic mode to shift the now of the radiation patterns to different directions. Those are excellent work for the pattern synthesis for single antennas. However, there's one drawback that in most of those literatures, the feedings are normally determined qualitatively by examining the current distributions or just by the experience. And there, besides, normally only one dominant mode is excited. If a combination of multiple modes are excited, it is difficult to find the feeding points or the feeding arrangement. So in this work, we are trying to provide a systematical pattern synthesis method for single antennas from the theory to implementation. And I think the main focus is on how to feed the antenna from theory to really make it practical. And as I think most of you have a basic background of characteristic mode theory, so I just briefly give an overview of this characteristic mode analysis. So as we know that the characteristic mode equation can be expressed like this. And why characteristic mode is so useful in the antenna field, I think one important metric is that its eigencurrents and the characteristic far field between different modes are orthogonal to each other. So we can design reconfigurable antennas, MIMO antennas, such so on. And for the pattern synthesis, I think there's one more important metric. That is, those characteristic far fields, they form a complete orthogonal basis for any pattern. What does it mean? It means that any pattern can be decomposed into the weighted eigenvectors or the eigen far field. So that is basic for the pattern synthesis for simple antennas. I will then describe the pattern synthesis method in an example. For example, the handset antenna. This is very simple and basic structure. So here is the structure. The structure here is just a simple 2D plate. Conducting plate whose dimension is 150 millimeter multiplied by 75 millimeter. And normally we know that for such a plate, rectangular plate, the very fundamental mode for this plate is the half wavelength dipole mode along the length of the chassis, which give us a radiation pattern, an omnidirectional radiation pattern on the XOZ plane. But that radiation pattern is not friendly to the user scenarios, especially the user's hand. It will make the efficiency very low when you touch it. So that is not our desired pattern. Our desired pattern is an omnidirectional pattern on the XOY plane, which is the plane of the plate. So we have the structure and we have now a desired pattern. What shall we do? The first step is that we calculate the characteristic far field of the first four modes, which are important modes at the frequency of 1 gigahertz. Those are the radiation patterns of those four modes. And then we calculate the weighting coefficient of those four modes to achieve the desired pattern. And thanks for Nikolai. Previously, he has already introduced us the relationship between the correlation coefficient and the weighting coefficient. So that's the way we calculate the weighting coefficient here. We calculate the weighting coefficient by calculate the correlation between the far field and the desired radiation pattern. With a weighting coefficient, then we can get the synthesized current distribution over the chassis. So those are the weighting coefficients we got for the first four modes. We can see that the third mode is dominant mode and the fourth mode also contribute to the radiation. So this will become our desired weighting coefficient vector. And then what is the problem to be solved here? One critical problem is how to feed the antenna to get this weighting coefficient. So this is a critical one. And we have a desired pattern. We just redraw it here. And we already got a synthesized current distribution with those eigencurrents here, this one. And we also have a relationship between the weighting, the feeding vector and the current distribution. So we can just directly calculate the feeding vector V from this equation. And this picture is the result of this calculation. We can see that the feeding vector is just distributed over the chassis. It means that we need to feed this chassis everywhere to get this desired pattern. This is not practical at all. So it is not okay for our real implementation. What shall we do next? So we are trying to find a method to reduce the non-zero elements in this feeding vector. And the method we use here is according to the concept of compressive sensing. So we use L1 or L2 norm to solve this problem. Physically, what does it mean? It means that we want to find the most sparse feeding vector V that can make the weighting coefficient as close as possible to our desired weighting coefficient. So with this feeding vector, we can see that after the L1 solver, we can have this feeding vector like this. It is much better than before. At least the feeding vectors are along the edges of this chassis. It's only on the 4 edges of the chassis. But this is still not enough. Oh, but one fortunate thing is that after this L1 solver, the correlation coefficient is still very, very high between the synthesized pattern and the desired pattern. But this is still not enough. We cannot have this continuous feeding over the edges. So the next step we take is that we just take the local maximums of those highlighted regions to be the discrete port. So we pick 4 individual port at the discrete feeding positions for this simple plate. And then we feed those 4 positions. And this is the feeding information, 2 feeding information tables actually. One is from the L1 solver and the other is from L2 solver. Different solvers can give us different results actually, but we can see that the locations of the feeding positions are almost the same. And those chart also shows the amplitude and phase of these feeding informations. By comparing those 2 tables, we choose the first one by L1, the feeding ports obtained by L1 solver, because it saves us 190-degree phase shifter, so we can make the feeding network less complicated. And this is what we got after we implement those 4 feeding positions into the chassis, and we carried out one in MATLAB and the other one in CST for real implementation. And now this pattern has a correlation of about 0.9 with the desired pattern. So one thing I want to stress here is that we can even further reduce the number of these feeding points, but the correlation will be decreased. So it depends on how you can, what is the standard you put there, or what is the correlation that you can stand with. So with these 4 feeding positions, we got 4 IC inductive coupling elements on the chassis, and the phase shift, the relative phase between the different ports are just according to the information in the table. And these are the topology of the feeding networks. With this topology, we draw these feeding networks here. It includes 180-degree phase shifters, power dividers, and quarter wavelength transformers here. So this is the front view of this antenna, and this is the back view. They are just on the same of the different size of the PCB. And with this antenna is matched, his bandwidth is from 0.88 to 0.94 gigahertz. And we can see that this parameter with and without hand, the antenna is little affected by the hand. So is the radiation pattern here. This is radiation pattern with and without hand in simulation. So it does not really affect the radiation pattern a lot. And then we fabricate the antenna. So this is the front view. We can see those 4 ICE feeding elements, and this is SMA connector. And this is the bottom view with the feeding networks. This is a matter reflection coefficient. We can see that it still works good in the low band with a gain of 2.37 dBi, and also it is very robust to other user effect. So this is just a simple case for the 2D structure, and we want to further generalize our method to a 3D structure, which is here a shipboard antenna. So for the shipboard antenna, for the ship-to-ship communication, normally it requires low elevation angle radiation patterns. So at very first, this is the scale structure of a real shipboard. And normally, the typical antennas for the ship-to-ship communication is a monopole-like antenna or a helical, something like that. So at first, we just put a monopole simply in front of the shipboard. And then we got a radiation pattern like this. We set this as a desired pattern. But in the real practical implementation, we really don't want such a monopole because it will be very, very high on the shipboard. So we get rid of this monopole thing, and we just have the shape of the shipboard. And then we calculate, we follow the procedure we illustrated before. At first, we calculate the feeding vectors using just a V equals Zj, something like that, the equation. Directly from the equation, we can see that this feeding vector is very distributed, and we cannot really feed it. Then we use the L1 solver to make the feeding vectors sparse, more sparse. Then we got this figure, the figure C. Then we can see that here there's less non-zero element in the feeding vector. And then we take the local maximums and choose only 3 feeding points like this. Now this is the result. We just put 3 feeding elements here. Of course, its feeding networks are also needed, and we use the ICE element to feed the antenna, and this is the radiation pattern we got. So from this shipboard antenna, we can use 3 feeding positions to achieve the main radiation on the theta equals to 50-degree plane, which well satisfies the low elevation angle requirement. And this pattern synthesis work has been published in early access in TAP in 2020. So I just use a picture to conclude my talk. So my talk here is talking about pattern synthesis. So what do we have? In the beginning, we have a structure, and we have a desired pattern to be synthesized. That is what we want our structure to radiate. Now, what shall we do? The first thing we do is calculate the eigenvalue, eigenvectors, and characteristic far field of the structure. And then we calculate the weighting coefficient of each mode through the correlation coefficient. Afterwards, then we use L1 or L2 norm to solve the problem to achieve a sparse feeding vector V. And here, since we have already changed the V, so we need to correlate the synthesize the pattern with the desired one. If this correlation is very large, it's much bigger than 0.9, then it's okay. Then we go to the next step. We take the local maximum of this feeding vector, and then we need to correlate the synthesis pattern again with the desired one. Here, if the correlation is larger than 0.7, I think this is what I said. So I think according to different scenario, it can be different, but it's just according to your understanding, and it will be okay. So then we'll try to see the feeding informations. What is how many feeding positions are needed, or what kind of power dividers and phase shifters are realized. Then we take a look at the feeding networks and compare the simplicity of the feeding structures resulting from different solvers, and then we'll choose a simple one. And the very last thing is that to put those feeding positions in a real antennas and match it using impedance matching network, or just to use a coupling element or something like that. Then you will get your desired pattern more or less. Okay, this will conclude my talk, and thank you very much for your attention.
Thank you so much for your presentation. Are there any questions for Huli? You can raise your hands in
I actually don't know how to raise my hand, but I have a question.
Just go ahead then. You can go ahead and then.
Yeah. About the V's, is there anything, did you see any effects regarding the size of your mesh cells? Because actually, I think V is obtained by the correlation of your basis functions, the RVG basis functions, to the incident field. And so V is depending on the actual mesh structure. And I'm wondering whether this is getting into effect if you just minimize V instead of E incident and not using the Gramian matrix here. Did you see anything like this?
Actually, for the same structure, we have tried different mesh, but we didn't try that for many structures. Just for this, for example, this simple 2D plate structure, and for the chipboard structure, I think we tried different meshes. It doesn't have much effect on the V vectors. I think it's. I understand your question that V is related with the RWG basis functions, but as Z and J is also related with that, I think the V after transferred to the synthesized current, I think it's not really depend on how you measure it, as long as it's not very, very coarse.
Yeah, I think it doesn't really depend on how dense you do it, as long as you do or let's say all of your RVG function as they have all the same size, it doesn't matter so much. But if you have different sizes in your RVG basis functions, then the Gramian matrix is not, how do I say, not evenly distributed, and then you might get some troubles here. Maybe, I don't know whether you're interested, but if you want to check that, you could mesh something with different sizes of RVG and see whether this has some effect here.
You mean that we mesh it in different regions, we use different meshes, something like that, and
yeah.
to see what is, okay, it's a good suggestion, and we will try to see that. Thank you.
Yeah,